So a little simpler title, 3D modeling of Crust and Lithosphere extension. So we started working on 3D models, I don't know, 12, 14 years ago. One of the first projects I had at University of Bergen involved both PhD student Vanita Alken and Cedric TLO as a postdoc. As part of that project, Cedric developed a 3D code that we called Phantom 3D. We first tried to use another code, but that wasn't very effective. And at the time, it ran in parallel on HPC systems, but we could only model crystal scale extension. I'll show you some figures from one of these papers because I think they're still relevant. And then more recently, we've been using Pitatin, which is developed by Dave May and colleagues, which is a very efficient, very scalable 3D code that runs on large HPC systems. And that the paper here on the bottom right is one of the first papers where we combine both the 3D tectonic model, but also the landscape evolution model Fastscape. That's coupled to it. So why would we want to do this? I mean, they're basically tectonics. There's many things you can do in 2D and many things we've done in 2D for basically, well, several decades now. But obviously, there's some features that we cannot resolve in 2D. And here we see North Sea, Vikengraben and Canyonlands, 3D segmentation of both systems. The North Sea is obviously a lithosphere scale rift. Canyonlands is a very thin sequence, around 800 meters of sandstones that are extended. But basically, we see similar features. And for this, we need 3D models to understand how these rift segmentation might evolve. So with Vanita, we used very simple models, crystal scale models, both with only a brittle layer and with brittle ductile layers. And the parameters that we varied were basically we seeded these models with weak seeds, as you can see here, the gray lines, and we varied the spacing between these seeds and the under or overlap, and got quite interesting results. So here's a set of models where you can see basically rift offset in horizontal on the horizontal direction, so from 0 offset to 6 layer thickness offset, and vertical is time evolution. Now we see here on the bottom that we get actually quite interesting variation of structures. One of the typical things we see in moderate offset, if you look at the 2H offset here, we see that these rifts, they propagate towards each other and they create these horsts in between the rifts. If we increase offset, we see that we get overlapping rift segments with a secondary graben in between. And if the offset is too large, they actually don't link. But we get this nice structure in between, and we have these sort of curved, rotating, propagating rift arms. Now, these models, we use them to compare to Canyonlands, among others, and we see that for these moderate offset rift system in nature, we actually have this similar feature, a horst that's basically forming in between two overlapping normal faults, linking the two grabens here in the upper panel, and in the lower panel we have the secondary grabens for larger offsets. Then we basically coupled that model, Phantom 3D, to Cascade, which is an old version with Philip Steer. And much of the work that I'm going to show you after is basically inspired by these first set of models that Philippe and me run while Philippe was a postdoc here in Bergen. Unfortunately, we were both very busy, and so these results were never published, but I should acknowledge the work we did at that time, because it basically is the basis for what we've done more recently. So in the last couple of years, we've spent a lot of time working with Dave, May, and with the 3D CFD code Peter 3D, which is massively parallel. The essential elements are that it has an ALE formulation, uses multi-grid, has a free surface. At the time, this is actually an older slide, we didn't have any surface processes, but we have coupled now Peter 10 to Farscape, which is a landscape evolution model developed by Jean Brown in a recent project. Typical model dimensions, at least for the models that I'm going to show you, is horizontal 500 kilometers by 250 and 250 kilometer deep. And this is real high performance computing. We typically run these on HPC platforms that we have available in Norway, around 4,000 cores, and need to run this for several days at least. Typically 100 hours, 150 hours is what we use for a single model. So here is the setup of these more recent set of models. We have a model domain here in the center with two inclined seats. We used inclined seats because basically we see to see the inner normal faults. We actually know from models where we have a symmetric seat that it's also the inner faults that link and preferentially form. And we varied multiple parameters: the offset between the seats, the surface process efficiency, the strength of the crust. And I'll show you two examples in the next two slides, and then an overview of the model results after that. As I mentioned before, we coupled the model with the landscape evolution model Farscape that basically takes the tectonic model topography and modifies it by the predicted amount of fluvial erosion and deposition. In these models, we have both continental deposition, but also marine deposition. That is mass balancing with the amount of eroded mass in the models. So here is the first case. It's a case of with 70 kilometer, a moderate offset. We call this 70 kilometer offset between the seats. The crust is strong, moderate erodibility. So if I run this, we basically see very quick rift flank uplift on the sides. I'll run it again. The other feature that we see is that we have in between the rift segments a horst forming where the two normal faults overlap, right? Okay, now actually my mouse is working. There's a basically normal fault that's dipping here to the left, and here on the bottom it's dipping to the right, and in the area in between these two normal faults overlap and they form a horst in between them, which is a very characteristic feature that we also saw in the crustal scale models. Now, in the next example, actually we see basically strain rate and plastic strain and cross sections for the models, where we also see this left dipping normal fault here at the top and the right dipping and the horst here in the middle. In the next case, the only thing I'm changing is the fluvial erosion coefficient, KF. And we see that this
10 minutes.
Yeah, that's fine. Thank you. We see that actually this changes the model behavior. It removes this tendency of forming a rift, And instead, we have something that's almost like a transform fault-like structure here in the middle. So just to stress that the only difference is the erodibility. Crustal strength is the same, offset between the seats is also the same. So here you can compare these two cases in more detail. I invite you to look at the paper if you're interested. It's published early last year. Again, formation of these horsts here in the middle on the left, which is a quite prominent feature, and that feature is removed when we increase the erosion efficiency. Here's an overview of all the models that are part of this manuscript. Model 1 and Model 4 here on the left are the ones that I just showed. If we increase the offset, if we, for instance, go down to Model 3 and SM2, we see that basically there's no linkage and one of the branches basically wins. But interestingly, if we lower the strength of the crust, we also see that the rifts don't link as efficiently. The base case here in the center on the left is these two rift segments that link with a central horst. If we decrease the offset or decrease crustal strength, and we basically remove the horst and have inefficient linkage. If we increase erosion efficiency, we also remove the horst and form a transform-like structure, basically again not link the two rift segments. We compared some of these observations from these models with features that we can observe in the East African rift. And here, especially if you consider the sections in the north, my mouse is not working efficiently, so I'm just pointing you to the locations AA and BB. We see basically overlapping rift segments with horsts that can clearly be identified in seismic sections. In the south, we have two segments that actually haven't linked because the offset was too large. So some of these features can also be observed in real systems. Now, lastly, before going to my conclusions, just an outlook of things we're working on now. The models that you have seen before, they basically dominantly focus on continental rifting. And we're using these models now to look at oblique margin formation. This is one snapshot from a set of models that I'm working on with Thomas Teunissen, and that he has presented at various places and that we're writing up. So I'll go to the conclusions. I should say that around 15, 18 years ago, 3D modeling was like the holy grail that we couldn't manage. Extremely challenging topic, both because we didn't have suitable codes that could efficiently solve the system of equations in 3D. We didn't have access to HPC platforms that we have now. We've gone through several generations and actually made a lot of progress, and well, actually it's quite an exciting time for 3D modeling because we can do a lot more. They're still limited. It's not like resolution is endless, but at least we can use these models now to look at various aspects of rifting, mountain building, tectonics, surface processes, etc. Furthermore, what you've seen is that we have a range of rift linkage structures that depend on offset, crustal strength, surface process efficiency, and other things that I'll leave you to read. Thank you.
Okay, thanks a lot, Ritske. So yeah, if you have questions, you can raise your hand. You can also use the chat. I have a question, but I can see already that Derek also have one. If you want to ask your question, Derek, yes.
Yeah, thanks. Thanks very much for the great talk. I was wondering, the models that you presented and ones that I've seen from other people with rift linkage, they commonly have just two segments linking together. What's sort of what needs to happen to make these sort of multi-segment scale models that have multiple segments to sort of see controls on the segment length coupled with linkage?
Well, that's not an easy question, but I mean, in these models we need to seed them, whether it's the crustal scale models or the very large scale. They all need various degrees of inheritance, and so I mean and I think it's not unreasonable that I mean the Earth, the lithosphere, is actually characterized by this. But so if we need for larger offset, we need also significant weaknesses. The last model that I showed was actually preceded by a large series of models where we tried to form transform faults, basically self-consistently, which is not very easy. And I think other colleagues have come to similar conclusions on that. So I think we need weaknesses.
I think I can ask, well, I have several questions, but I think I can select one. So you showed models with these initial faults located in the upper crust. Did you do some tests with equivalent heterogeneities, but in the mid crust or in the lower crust?
Well, yes, we did. We actually put also weak seeds in a mantle, which I mean has a very similar role. I think the main thing where weak seeds are not very effective is when you put them in weak viscous middle or lower crust.
Yeah.
And then they're basically not seen. So you have to perturb the strength of the plastic or brittle layers, if you wish.
And if you put them in the brittle layers, like for example in the upper mantle, the wavelength would be the same type in your 70-ish kilometers. That would be the same rule.
Yeah.
Okay.
So, yeah.
Interesting. And I think I have time for a last question. Did you do
yeah, go ahead.
Did you do also some tests varying the extension velocity and doing, for example, some tectonic poses?
We did that in 2D. I mean, you have to realize that these 3D models, they are quite expensive. I mean, they don't cost money yet, but they take computing time. And so it's not like you can run thousands of them. But in 2D, we did this. And I mean, the extension rate is not such, at least we didn't do the forces, but we basically had varying rift duration. And this is especially interesting when you link to surface processes, because then basically you might have a different time lag between surface processes and tectonics.
Yeah, exactly. Yeah, that's it. Yeah.